One of the more difficult concepts to understand is molecular orbital theory. Here's a simplified version when we're talking about hydrogen. The hydrogen is the simplest of all elements. It consists of a single proton in the nucleus, and outside the nucleus is an electron cloud that has a single electron in it. And so you have a positive charged nucleus surrounded by a negatively charged electron cloud. This electron cloud, well, the electron itself exists in what's called an orbital. Orbitals are basically probability functions where the likelihood of finding an electron is. In this case, hydrogen is the simplest of all elements and has the simplest shape of an orbital, which is the s orbital. The s orbital is essentially just this sphere. So the hydrogen atom can almost be approximated as a sphere. Its radius is about 1.2 angstroms. This is what's referred to as the van der Waals radius, where if it bumps into something, that's about the closest that the two nucleuses can get to one another, unless, of course, there's a bond involved. And the reason it's very difficult for two hydrogen atoms to come together is you have basically these two electron clouds, which are both negatively charged. And negative charge has a tendency to repulse each other. But here's the thing. If you sum two van der Waals radiuses together, you get a total of 2.4 angstroms. So that's this atom and this atom. Here. So the distance between two atoms just briefly touching each other, two hydrogens briefly touching each other, is 2.4 angstroms. Thing is, hydrogen gas itself, H2, the bond distance between the two nucleuses of hydrogen has been measured to be 0.74 angstroms. Much, much, much less than 2.4 angstroms. This is a chemical bond. Specifically, it is a covalent bond, where the two atoms are sharing their electrons in such a way that it actually brings their nucleuses closer together than they normally would be. Here's how it works. Important thing to remember is that electrons are so small that they exist both as particles and as waves. And waves have phases to them. You have a positive phase and a negative phase. Positive, negative, positive, negative, and so on. This has nothing whatsoever to do with charge. Electrons are always negatively charged. This phase only has to do with the phase of the electron it is currently. So, if you have two atoms coming together, one has one phase and the other one has the opposite phase, well, the way we show one phase, we can draw it like this. And if we show the other one as an opposite phase, we'll just shade it like so. And so, instead of the two lining up perfectly, they line up opposite each other. So when this is at a peak, this is at a trough or so. If you were to add these two together, you get basically summing those two electrons out. It's almost like they didn't exist to begin with. So if you have this situation where they are in opposite phases of each other, it's like the electrons suddenly disappear from our universe altogether. And so they're no longer there, which means you have suddenly a case where we have a proton and a proton, two positively charged centers right next to each other, and there's nothing shielding these two nuclei from each other, and as a result, these hydrogen atoms go their separate ways. They try to get away from each other as far as possible. This is what is referred to as an antibonding interaction. These are very high in energy. They are essentially destabilizing forces. But if you take a look at the case where they come together in the same phase, like so, add them together, what you get is constructive interference. It's almost like there's more electrons between them than they really are. And so you have an H+, positively charged nucleus, positively charged nucleus, and suddenly you have lots of negative charge between these. This causes the nuclei to come closer together, because now you have more negative charge shielding the two nuclei from each other, causing them to get a little bit closer. This proton gets closer, this proton gets closer. As a result, the two atoms smash together closer than what their van der Waals radius normally would allow. This is referred to as a bonding interaction. This is low in energy, and it's basically a stabilizing force.